So let's see if we can use this idea of replacement and mapping notation on an actual function. Instead of just f of x and flipping things back and forth, let's take an actual function, which I just happen to have here, is x squared minus 2x minus 3. Let's see what happens. It says sketch the graph and then sketch the graph after the transformation. So if you look at this one, of course, here's our x horizontal. So we're going to flip this on the horizontal across the y-axis. And this one is both. Both are reflected. So we got two negatives. We've got a horizontal one and we've got a vertical one. Oh my goodness. Okay, so one thing at a time. What we might have to do is let's take a look and see what this graph looks like right off the bat. Okay, so what I would do is I would pull out the old calculator and I'll put that into the calculator right now. So here's my calculator. Oh, there it is. Put the y equals 2 there. I've got my x squared minus 2x, x squared minus 2x, and minus 3. Let's see what this guy looks like. Let's graph it. Boom. Hey, look at that. That looks kind of nice. We've got a couple very important points. We can see one of the points right here at the -1. So that's probably a 0 there, or an x-intercept. And I've got another one out here that looks like it's at about 3. So you know what we could have done? It saved ourselves a little bit of time and just quickly factored this guy. And we found out that that's x plus 1 and x minus 3. Well, we could have done that by inspection. So there's the -1, which remember takes this x plus 1, lets it equal to 0, becomes x equals to -1. And this guy, which is x minus 3 equals to 0, giving x equals to plus 3. There it is. But my question is, where's the vertex? Since we're on this kind of roller coaster ride with algebra, let's just figure out the vertex. And maybe that'll give us a chance to look at something called completing the square again. That's right, complete the square so it becomes in vertex form. Let's see what that does. Now, you might want to dig up an old podcast from the Math 20 here to figure out how to do this again, because I'm going to do this quite quickly. After all, it is Math 20. X squared minus 2x. Remember, the one that doesn't cooperate is the one that you throw out of the house. There we go. Half of this becomes -1, and that's our magic number. Okay, square it becomes +1. If you add 1 here, you got to subtract 1 there. Here we go. Now we can write this in beautiful form. We know that this is x minus 1. There's the perfect square, because after all, this equation is now a perfect square. You made it that way. -3 and -1 becomes -4. So there's your vertex at 1, -4. Look at that. 1, -4 is going to be all the way down here. Let's use red. Boom. Oh, and here comes our nice parabola. Looking really pretty. Look at that. Oh, that's gorgeous. All right. So now let's do the first reflections. Let's talk about this reflection right here, which is the horizontal reflection. We're going to do that first. So guess what? I got a whole bunch of points that I can play around with. Yay, yippee skippy. But we also want to point out one other point, which I think is kind of neat. Remember this guy? Do you remember what that means? Probably not. Go back to Math 20 and look at one more podcast. But if you realize something, that's actually the y-intercept. So the y-intercept is at -3. So I'm going to put that point in there as well, because that's going to help us an awful lot. Okay, now let's remember, we're going across this, which means we're doing a horizontal across the y-axis. So guess what? There's your first invariant point right there. That point doesn't change because that, of course, is our mirror line. Yay! Okay, now let's start looking at the other points. Let's start with this one. 1 to the mirror, 1 over. There's your new vertex. Look at this. 1 to the mirror, 1 over. There's your other point. Look. 1, 2, 3, 1, 2, 3. Look at that. So all of these points have now suddenly come around like that and up through there. There's our first horizontal reflection. But now we have to look at the fact that we want to do this horizontally and vertically in this section right here. Okay? Well, guess what? you've done the horizontal already. Why don't you just take the green graph here and just flip it vertically? You can do that as well. Why not? Okay, so let's pick another color. Here's another color. And remember, in a vertical flip, okay, that becomes the mirror line. Okay, perfect. There's -4. Well, that becomes +4. Look at that. Invariant points. Uh-oh. Why? Because remember, the invariant points are now the x points. Whatever the mirror line is, whatever's touching the mirror line, those become the invariant points. Okay, and then finally, you can actually even take this -3 and put it up to the +3. And look how beautiful a graph you have. This one's not only just flipped horizontally, it's flipped vertically as well. So this is going to make some interesting stuff here. So I put a nice little chart here down here to kind of keep things all kind of in order. Remember our domain. Our domain for a function like this, remember, x is an element of R. Why? Because you can put whatever x value you want into this equation and you're going to get a y out. Now, range, on the other hand, take a look at our original red graph, which is this is our original function right here. Okay, do you remember? Okay, so look, the domain and range. The range then, you have a minimum point. You have a minimum, which means, guess what? All values above that minimum. So your range has to be all values of y that have to be greater than and equal to -4. Your intercepts, we figured those out from, guess what? Factoring, right? There's our intercepts, -1 and 3. So let's put those down. X equals to -1 and 3. There's your intercepts. And then finally, don't forget the y-intercept is just this little guy out here, all by its lonesome, because remember, that happens when x equals to 0. So if x equals to 0, that's 0, and you're left with just plain old y equals to -3. Oh, isn't that cute? Okay, so let's see what happens now when we flipped it. And I'm going to do this guy first. Let's see what happens when we flip this horizontally. When we flipped it horizontally, let's look and see what happens. If you noticed, when we flipped horizontally, and this is the green line here, okay? Notice something. Domain didn't change. The minimum value didn't change. The y-intercept didn't change. The only thing that changed was our x-intercepts. Isn't that interesting? Okay, so let's go back to here. Our domain is still an element of R. You can put whatever number you want in for x, it'll work. Your range is still greater than or equal to -4. Isn't that interesting? Your intercepts, because you flipped them horizontally, means you have to change the sign on all of the x's. So look, this becomes 1, this becomes -3. Isn't that interesting how they flipped from this and this? Wow, cool. Okay, your y-intercept hasn't changed. Your y-intercept is still -3. Very cool. Now, let's flip them vertically and horizontally. Well, I'll tell you right now, domain hasn't changed. Your range, because now if you think about it, the orientation is different. The orientation is upside down. So now you've got a maximum, and your maximum is at 4. Okay, so that means y has to be less than or equal to +4. Your intercepts, let's see. Your intercepts are these. And why? Because you did both. You not only flipped it horizontally, you flipped it vertically. So guess what? Bada bump and bada bump. And of course now, look at your intercept. Look at your intercept. Your intercept is also flipped because it's a y-intercept. And when you flip vertically over an x-axis, guess what? That changes. So what a really cool group of questions for you to look at.